Next presentation by Guillaume Henderson from Ghent University in Belgium will be about lithium extraction from natural brines through membrane electrolysis with limited waste generation.
Thank you. I'm going to stand on this side. Perfect, it's working. So, hello, my name is Guillaume Henderson. I'm from Ghent University, and I will be talking about our project, Lithium plus Water, that we've completed now in our group, which is about lithium extraction from natural brines through membrane electrolysis with limited waste generation. I don't think I have to explain you anymore why we're here and why lithium is important. You all know this. The only thing I'm gonna re-mention again, because Magdalena already did it, is what you can see on this curve here, and that is basically the projected supply and demand of lithium. And as Adam Smith has stated so many years ago, if you have a demand that is way too high that your supply cannot follow, the price will explode. And that is what is already happening with lithium right now. As you've seen, in almost 2 years' time, the price exploded and it multiplied by 14. So we really need to increase the mining capacity to be able to meet the demand of lithium, not only now, but also in the future. So then, if we have a look at where our lithium nowadays is coming from, most of the lithium is being mined and exported from Australia to the rest of the world, where it's extracted from mineral rocks, but the majority of the lithium is actually located in South America, which is represented by the green bars, and in the region which is called the Lithium Triangle, which is located in Argentina, Bolivia, and Chile. And there you have lithium that is present in the natural brines, as we so call them, and these are very salty waters, which have about 10 times concentrations of seawater, and are located in lakes in the Andes Mountains. They have impurities, or let's say other ions present in the solutions, but they're much less complex than geothermal brines, and they also have higher concentrations than geothermal brines, and are therefore considered to be a bit more easy to extract lithium from, and therefore also mining companies are already doing or extracting lithium from them. So, how is it being extracted from these brines nowadays, lithium? Well, this is a picture of a company that's located in Argentina, the Sala de Olaroz. And so they pump up the brine from these ponds, and they're going to put it in here in the evaporation ponds to then use sunlight to concentrate the water, and they're going to use this an evaporative/solar process. So how does it work? Here is a bit more in detail. So you have sunlight. So first you're going to pump up the brine, then you're going to use the sunlight to evaporate the water and concentrate your brine. With that you're going to precipitate some impurities or other ions that are present in there, like sodium, magnesium, etc. You're going to add chemicals to precipitate more ions, etc. You're going to use more sunlight. So basically what you're going to do is you're going to use sunlight, you're going to add chemicals to precipitate impurities, and then recover finally lithium as lithium carbonate. However, what you should know is that this step of evaporating can take 1.5 up to 2 years time only to complete to then further process your lithium. So if you want to expand our production rate, with these methods, they're pretty slow and maybe not quick enough to meet our supply of today and tomorrow. Besides that, they're also very devastating for the nature, because you evaporate all the water from the region, which is already a very dry region. You can lose up to 50% of the initial lithium that is present in these brines, and per ton of lithium carbonate, you're producing 115 tons of waste that is only be landfilled. So we really need alternatives for that. And so here you have an overview again of the process that we use, that is being used, sorry. And what you see is that if you want to create a new process, you need to take 3 things into account. You need to concentrate your brine to concentrate your lithium. You need to make changes in pH to remove other ions and to be able to selectively extract your lithium. and you need to add as well some carbonates right now to be able to separate your lithium from your sodium. So what did we propose, or what were we looking into? Membrane electrolysis. For you, those of you who don't know yet what is membrane electrolysis, well, you have an electrochemical cell, just like you are using for hydrogen production, for example. You have a cathode, you have an anode. At your cathode, you're going to have a reduction, so you're going to form hydrogen and hydroxides. So the pH of this compartment will increase. And at the anode, you will have an oxidation, so water oxidation to form protons, or in our case, as we have chloride present, we can form chlorine gas. Now, in our case, we use an anion exchange membrane that separates both compartments, and when you apply a current, the chloride ions will migrate over your membrane together with some water to then accumulate in this compartment or form chlorine gas. So this membrane electrolysis tool can thus concentrate brine, you can make changes in pH, and you can add carbonates, then afterwards by, for example, flushing CO2, so to then to precipitate lithium as lithium carbonate, or sodium as sodium carbonate, or sodium bicarbonate. So then a bit more about the separation between sodium and lithium. If you look at our chemical equilibrium diagram that we simulated, we see that with the current concentrations we have, at elevated pH ranges, we can precipitate lithium as lithium carbonate without having any sodium precipitates, and at medium pH ranges, we can precipitate sodium as sodium bicarbonate. So we can, depending on the pH range, we can selectively extract our lithium and sodium. And that is what we try to implement in our method. So if you then go back to the raw brine, you have some calcium, magnesium, boron, and all the other elements. And so you start with your brine. The first thing you have to do is you have to remove the boron, because if the boron is then later on still present and you have some precipitates, for example of calcium and magnesium, lithium can be trapped in the crystals, so you lose some lithium. That's why you first remove the boron. And then you're going to remove the calcium and magnesium, because if they're still present in your electrochemical system, they can form precipitates, they can clog your membranes, so your membrane electrolysis cell will not last very long. So after these are removed, you have your solution with sodium, potassium, lithium, and chloride, and you're going to send it through your electrochemical cell. So the first approach was we first use our electrochemical cell, we absorb CO2, we precipitate sodium as sodium bicarbonate, then we have a more concentrated solution with less sodium, more lithium present, so we could recover more lithium. And in a second approach, we went first for lithium and then for sodium. Now, the first approach we thought was going to be the most interesting one, but it wasn't, because in fact we were losing lithium throughout the crystallization of sodium bicarbonate. So we are running our electrochemical system with a side crystallizer. The pH, the bulk pH is 8.3, so in theory we should not have lithium carbonate crystals, but we were precipitating it, and as you can see on the graph, the black line, it's decreasing over time, because at the cathode surface you have a very tiny layer with elevated pH, because that is the place where your hydroxides are formed. So because of that, there your lithium carbonate could form, crystallize, and then you lose lithium out of your system. So therefore we changed our approach, and we went first for lithium removal and then for sodium removal. So here again our electrochemical cell, so we first are going to go for a very high pH, so we go for 14.5 pH, after which we can then absorb CO2. And at the same time we're concentrating our brine. We are, as you can see here, there is water migrating from your cathode to your anode, which means that the concentration in your cathodic compartment will increase over time. And because of the very high pH, you can then absorb very efficiently CO2 as well. Then for the lithium, so here you can just see the concentrations we were obtaining. And then for the lithium crystallization, lithium carbonate, we do that, and so we flush CO2 until we reach pH 11. And then at a temperature of 88 degrees Celsius, we're going to crystallize the lithium carbonate. We could recover at two different current densities from our electrochemical cell every time approximately 70 to 74% of our initial lithium. with a very high purity, already 98.5, without any washing steps or additional washing steps, which is very high already, higher than the current evaporative processes. However, our energy consumption was still very high, as you can see, and with the current gas prices, we should really improve that. Then we could go at the same time without adding extra current. We could just lower our pH, and with the remaining carbonates, we could recover sodium as sodium bicarbonate, and we could recover 28.5 or 22.5% of our initial sodium, or as you could see here, approximately 2 kilograms, 1.9 kilograms of sodium carbonate per kilogram of lithium carbonate, which is valorized, which you can sell, or you can use in our system in a prior step as shown here. So here, just again, conclusion, the general flowchart we designed. So first boron removal, calcium magnesium precipitation and polishing, to then with an electrochemical system recover lithium and then sodium carbonate. So we use the membrane electrolysis process, which is not weather dependent, and there is no water being lost from your ecosystem. You can just continue to process water or re-infiltrate it in your salar. No chemical addition except CO2, and we are not producing any waste. We're valorizing our waste as byproducts. However, yeah, well, as drawbacks, we could say that we still have CO2 present, and the energy cost is still too high, which we are working on in the future. So, thank you very much for your attention, and if there's any questions, shoot, I would say.